Welcome back. This is Discrete Math Lecture 10. This is going to be a quick look at set operations. Okay, so we're building on top of our introduction to sets last time, and now we have different operations that we can apply between two or more sets. Okay, so the first one that we're going to talk about is called the union. Let A and B be sets. The union of sets A and B, denoted by A with this little U looking symbol, B, is a set that contains those elements that are either A or B. Okay? And we can see in this definition here, A union B is, in set builder notation, the set of all x such that x is in A or x is in B. Okay? So the union is the same thing as, well, it's the set equivalent of our disjunction from logic. Okay, so this is that or property. So visually on a Venn diagram, it's going to cover any elements in here or in here or in their intersection, right? So any elements in A or B, including their intersection as well in the middle, right? So for example, if we had set A contains elements 1, 2, and 3, B contains 3, 4, and 5, A union B is simply putting all of those together. 1, 2, 3, 4, 5. Now you notice 3 is a redundant element. It's within their overlap. We just need to list it once. Okay, we're always listing sets as their, in terms of their distinct elements. Okay, so that's A union B. Next, we've got the intersection. Okay, so this is the other big operation regarding sets. The intersection of sets A and B, denoted by A with this little N looking symbol, B, is the set containing those elements which are in both A and B simultaneously. Okay, for our definition with set builder notation, we've got the same thing. For all x, this is the set of all x such that x is within A and x is in B. Okay, so this now is our set theory equivalent of the conjunction. So union was or, intersection is and. Okay, if we use the same exact sets from above, A is 1, 2, 3, B is 3, 4, 5. If we're looking for A intersection B, it's only going to be that element which is in both A and B, and that will be the 3. That's what falls in the middle on this Venn diagram. Okay. So that's intersection. Now, given this idea of the intersection, this concept of the intersection, if the intersection of sets A and B is empty, then they are what's called disjoint sets. Okay? So if A had the elements 1, 2, and 3, B had the elements 4, 5, and 6, well, they don't share anything in common. They don't overlap at all. And you can denote their intersection as the empty set. Okay? And their intersection contains nothing, no elements. Okay? So that's just disjoint. Okay? So that's a special case of intersections when sets have nothing in common. Okay, next we've got what's called the difference. The difference of A and B, denoted with this little subtraction symbol, right? Same thing, minus. This refers to the set containing everything in A that is not in B. So it's almost like we're doing A, take away whatever is also in B. Okay, what is exclusively in A? That's what we're looking for here. The set builder notation definition of this is the set such that for all x, x is in A and it's not in B. Okay, x is within A and it's not in B. Similarly, if we had B minus A, it would go the other way, and it would be whatever is in B and not in A. Okay. So for example, we've got A is the numbers 1, 2, 3, 4. B is 2, 4, 6, 8, the even numbers. If we subtract these, A minus B, we're going to have to take out those even numbers from A. We'll just be left with 1 and 3. Okay, so this is an operation that will allow us to isolate within some set and cut out some intersection. Okay. Then we've got the complement. Okay, so the complement is really just your set theory equivalent of the negation. Okay, so the complement of a set A, denoted by A with this little dash over it, is the set U minus A. So another way of thinking about it is this is the difference between the universal set, your entire rectangle, and then cut out whatever was an A. It's everything else. It's everything outside of that. It is the set of whatever is not an A, but still within the universal domain. So A complement is defined as X is within your universe such that X is not in A. So if our universe was the numbers 1, 2, 3, 4, 5, 6, A has those even numbers, 2, 4, 6. Not A is going to have all of the odds, 1, 3, and 5. Okay? That's a simple idea. It's just the opposite of whatever is in A. Right, so now let's look at some examples. So let's suppose we've got this universal set. X is a positive integer such that X is less than or equal to 10. So that means it's going to be the numbers 1 through 10. That's our universal set. A is going to be a subset of that. And it's going to be everything up to and including 5. B, same idea, but this is going to be the numbers between 4 and 8, including 4 and 8. So now, here are 10 combinations or instances of the usages of these different operations, some of them together. So we've got A union B, A intersection B, A complement, B complement, the intersection of the complements, the union of complements. 7 is going to be the complement of the intersection. 8 is the complement of the union. So the main operator has switched, okay, between 5 and 7. Here, the main operator is the intersection. Here, the main operator is that complement. And then 9 and 10 are just the differences. A minus B and B minus A. So take a moment to try these 10, given your sets U, A, and B, and see what you can come up with. All right, now let's look at the solutions to these. So just like we said, U is going to be the numbers 1 through 10, the integers 1 through 10. A is 1 through 5. B is 4 through 8. So our first one says A union B. Well, we're just putting together all of the elements of A, all of the elements of B, including their intersections, but there's no need to be redundant about them, so we're just going to have the numbers 1 through 8. These are all of our distinct values. Okay. Number 2 is A intersection B. Well, that's going to be just those overlapping elements, 4 and 5. Number 3, A complement. Well, it's going to be everything in the universe that is not in A. Okay, so A is the numbers 1 through 5. Well, A complement's got to be 6 through 10. Then. Okay. B complement, similarly, it's going to be everything in our universe that's not in B. So we're going to wipe out those middle numbers. We're going to be left with 1, 2, 3, and 9 and 10. Number 5, the intersection of the complements. Okay, well, here are our complements, numbers 3 and 4. to find the intersecting elements. We're just looking to see what they have in common. They just have 9 and 10 in common. So the intersection of A and B complements are 9 and 10. Number 6 was asking about the union of the complements. Okay, so now we're putting together whatever elements we have in number 3, whatever elements we have in number 4. Let's put them all together, and we'll just list them as distinct elements. No need to relist redundancies. So we've got the numbers 1, 2, 3. We're going to skip that 4 and 5, and then 6 through 10. Okay, because there's no 4 and 5 that shows up in either of these. Okay, number 7. Now, number 7, like we said, this is taking your intersection and then doing the complement of your intersection. So our intersection in number 2 was just 4 and 5. So if we go to the universal set, it's going to be everything except 4 and 5, right? So it's going to be 1, 2, 3, and 6 through 10. That's exactly what we've got here. 1, 2, 3, and 6 through 10. Now, number 8 is asking about the complement of the union. So A union B was our solution to number 1. So the complement of that is just going to be the 2 numbers that are not included here. So within our universe, we've got numbers 1 through 10. We're not going to consider 1 through 8 as we had in 1. So our solution is just going to be 9 and 10. And you might notice that some of these sets are repeating. All right, so we're going to come back to that idea in a second. Let's just finish up here. So number 9 is asking for the difference of A and B. So everything in A, take away whatever's in B. So what they share in common is 4 and 5. So that will just be 1, 2, and 3 once we take those away. B similarly is everything in B, take away whatever it shares in A. It wants nothing to do with A. So we've got 4 through 8, and we're going to remove those overlapping elements, 4 and 5. So we're left with just 6, 7, and 8. Now, 5 and 8 are the same thing. They're both 9 and 10. Similarly, 6 and 7 are the same thing, right? They're 1 through 10. Both are missing 4 and 5. And this is no coincidence, okay? So our good old De Morgan's law is coming back. So De Morgan's law, which stated the negation of the disjunction, you can kind of distribute that negation and flip that disjunction, make it a conjunction. And the same deal with this, the negation of a conjunction, you can distribute that and flip that conjunction into a disjunction. The same law applies here. So set theory is built off of logic. So all these relationships still hold. The same operations are being used here. The same relationships will come up. Okay, so the complement of A union B is the same thing as the intersection of the complements. This is like your disjunction. This is like your conjunction. And the complement of your intersection is the same thing as the union of your complements. All right, so these are just your De Morgan's laws coming back over here. All right, and finally, let's talk about the cardinality of the union of two sets. So cardinality, if you remember, refers to the size of a set. How many elements does it possess? We can use what's called the principle of inclusion exclusion to determine this cardinality, right? So for whatever reason, we don't have access to the set of A union B, or it's too large or too unwieldy to determine the cardinality of it in a straightforward way, but we do have these elements. We can put these together and figure out that cardinality of that union. So this is saying that the cardinality of the union of A and B is equal to the cardinality of A plus the cardinality of B minus the cardinality of their intersection. Okay, this is an important relationship when we talk about probability this relationship is going to come back, specifically when we talk about the probability of events A or B. Okay, so probability, the same way set theory is built off of logic, probability can be built off of set theory as well. Okay, so let's see an example of how this might work. Suppose we've got set A is 1, 2, 3, 4. Set B is 4, 5, 6. Their intersection, of course, is going to be the element number 4. Well, then the cardinality of A is just going to be 4. The cardinality of B, we've just got 3 elements, that's 3. The cardinality of A intersection B, they've only got the 1 element in common. We don't want to double count it. We've already counted that element number 4 here. We've counted the element number 4 here. We don't want to double count it, so we're going to subtract it off. So we've got 4 plus 3 minus 1, and that gives you that the cardinality of the union of A and B is 6. Okay, so I've got the same thing worked out here. 4, 3, 1. And if we actually went ahead and constructed the union of A and B, well, it would just be the numbers 1 through 6. Right? We're not redundantly listing 4. We're just listing the distinct elements. And of course, this has a cardinality of 6, which verifies that this formula holds. All right, so this was a quick look at set operations, building on top of what we talked about last time with our introduction to set theory. So thank you for watching. Please make sure to like the video and subscribe to the channel if you enjoyed this so that you can see more content in the future.